So that's trig in a nutshell, and we'll move on to talking a little bit about coordinate systems now. So the next couple of topics is coordinate systems, and then we'll talk about vectors. So essentially, a coordinate system is how we represent a point on a 2D plane. So what we want to do is we essentially can represent it in two ways. We can either represent it as latitude, longitude type thing, or alternatively, we can also represent it as it is this far away from our origin point, and so it's this far away, and then we can also talk about the degree that it is away. So, it's at a degree of, let's say, 45 degrees to the plane, and it travels, how much is that? Like 4 in that direction. So we can either use that longitude, latitude, or we can use that distance, angle type situation, and that kind of gives us our polar or our Cartesian forms. So when we use our functions in like our normal universe, what we deal with is we just deal with our Cartesian universe, right? And this will become particularly relevant when we're talking about like complex numbers, which is the system where we use our polar numbers for. So that's the whole idea of it. So we will use our polar systems when we're kind of dealing with vectors and complex numbers, which are two of the newer topics which have been introduced, or not newer as in new to the study design, but new to people doing 1-2. So you will have not seen vectors or complex numbers before you do 1-2 Spec, and if you only do methods, then you won't see it for your entire VCE educational career, I guess. But because they're quite new topics, there's also going to be a bit of limited amounts that we actually do in each topic. So the one important thing that's kind of common to both of them is that use of that polar system to talk about either distance. So in vectors, we'll be talking about the magnitude and then the direction. And in complex numbers, we'll be talking about in polar form. So there is a polar form for complex numbers. So how we convert polar to Cartesian is essentially we can just use x equal r cos theta and y equals r sine theta. And the reasoning behind that is essentially because if you imagine like our plane that we did before and we have a point here, right? We can kind of draw like a pretend triangle there. And because the triangle is going to be right angles to the axis, we can essentially have like an angle here. So we'll say that, it's 45 degrees of unit 3, or was it unit 4 before? And so we know that this line would have been 4, or for our purposes, it's going to be r, which is like the radius per se, so that how much it's radiating out. So if we use that, right, if we know what r and theta is, so if we want to kind of talk about that point in Cartesian form, so you want to find the x, y, essentially your x will be along here and your y will be along here. And one way to find it is just using that SOHCAHTOA, right? So SOHCAHTOA, because our x is just going to be our adjacent and our y is going to just be our opposite. So our adjacent over our hypotenuse, so x over r, is going to equal to our cos theta, and our y over our r is going to equal to our sine theta, because it's our opposite over our adjacent. So you can kind of see how that's converted into this. And then in terms of Cartesian to polar, so the other way around, so if we draw our axis again, and then we have, a dot here, and we know what x, y is, once again we can draw out a bit of a triangle. And if we wanted to find what that r, so how much it needs to travel to get to that point directly from origin, we can just use Pythagoras, so that's x squared plus y squared, so a squared equals to b squared plus c squared, and that's just derived from there. And because our r is always going to be a positive value because it's radiating, it's just telling you how far it's moving. And then our theta, there's a couple of different ways to do this. You can divide it by r as well, but probably the easiest one, which requires the least assumptions in terms of you've done your values right, is going to be the tan one. So what you can do is you can just make the tan inverse, because your theta is going to be here once again, and it's going to be y on x, your opposite over adjacent, and so you can just do tan inverse of that. And use your logic as well to figure out whether it's supposed to be, an obtuse or an acute angle. So we can kind of think about this. So they want us to convert this following function into a Cartesian form. So what we can do here is we can say that y equals to r sine theta. So that's going to equal to this tan theta sec theta times our sine theta, right? So what we can do is we just go our sine theta times our 1 over cos theta, because that is our sec, and then times our sine again. So you can kind of see how these two would kind of go to sine squared theta at the top, and the bottom would go to cos squared theta, as this, if we think of where it sits in the triangle, where it sits in the unit circle, it's going to be here, right? And cos is positive in that direction anyway. So you're going to get sine squared theta over cos squared theta, which is tan. Let me just clear that sheet. Erase all ink. So then for our x component, we're going to do the same thing except times by cos. And so we're going to have the cos cancel out there, and it's just going to be sine over cos left over. So we're going to get tan. So if we wanted to write it in Cartesian form, or convert it to Cartesian form so that it's a function instead, you would just get that y will equal to this and x will equal to this. So y will equal to x squared. Alternatively, if you're looking at this in the first place, you can just go kind of put it into the two directions and then just equate them. So you can see how we can get functions from the same thing. And so we will never be expected to graph funky things like this, fortunately. They are really cool to look at though, definitely. So although we won't be expected to graph stuff like this, sometimes you'll see it draw on the pages already and they'll tell you, oh, this is a thing, right? So it's good to kind of just have a play around with Desmos and stuff just to recognize those different types of graphs. Okie dokie. Alright, so then how can we represent a path of a moving thing on a plane? So we can represent it via a function, right? So normally when we're in the Cartesian form, what we say is, this bus is moving this way, and we can kind of represent the path using a function type form. So we can do the same thing with all of the stuff that we've learned so far, so the polar stuff, right? And even more than that, we can also introduce the concept of having an exact position as well. And what that is going to be called is essentially using a paradigm to help us tell us what's going on. So instead of writing y in terms of x, just showing us what the path is, we can actually also find at what time it's going to reach that path, right? And t is going to be our parametric variable or our parameter. So what we can do is when we want to convert, right, the easiest thing to do here is essentially what you want to do is look at your y and x, and your goal is to get them. So there's kind of two ways to do it, and it just depends which type of function you end up having. The first way to do it is what you want to do is get your everything in terms of your parameter. So t equals to something, t equals to something. So t equals to something in terms of x, and t equals to something in terms of y. So that's one way to do it, and then you kind of equate them and then mix and match until you can get y in terms of x. Another way to do it is that you make them so you can identify a relationship between them. And this often applies when you're dealing with stuff like the trig stuff, so sine and cos. And that means just that you get stuff in terms of sine, get stuff in terms of cos, and then you can use your trig functions to kind of combine the two together. So generally what you want to do is you kind of want to eliminate stuff from both options, so you essentially can just substitute it back in, and then sometimes you can use trig identities as well. So one thing is that you will also see stuff sometimes which aren't relations, aren't functions, they're relations. So stuff like circles or ellipses or hyperbolas. So things like that just mean that you won't really be able to get, y in terms of x in a nice form. So it's okay to leave it in a form which is a bit more complicated, as long as it is the correct form for that type of relation. So for example, for a circle, it is absolutely great and fine to just leave it as like x squared plus y squared, or vaguely in that type of form. You can also do it by recognition as well, but it probably you can also, when you're converting back, you can do it by recognition, but also you can just essentially put in a parameter in some point. So often with relations with circles, there's kind of structured ones in terms of how you can do it. So for example, circles, they use a lot sine and cos. For ellipses or hyperbolas, often they might use sec or tan a little bit. For other things like parabolas and stuff, you can probably just make it up, and as long as you have the correct ratio of the variables, it doesn't really matter either way what you're really doing. Just use the simplest one you can think of. Okay, cool. So let's talk about this one. So the point moves according to the parametric equation x equals to t minus 2 and y equals to t squared minus 4t plus 1. Show that the Cartesian equation of this path is x squared minus 3. So I think that the easiest thing probably to do here would be to work on both of them and then put it all together. But for our learning's sake, we can just make our t in terms of our x and then kind of substitute it in. So what we're going to get here is that our t will equal to x plus 2, and we can substitute it in here. So y will equal to x plus 2 squared minus 4 x plus 2 plus 1. So you can kind of see I'm just substituting wherever t is sitting with our x plus 2. So what we're going to get here is we can expand it. So x squared plus 4x plus 4 minus 4x minus 8 plus 1. So what you can see here is we've got our x squared, our 4x's cancel out, so they're gone. We have 4 minus 8, which is negative 4, and then plus 1, which is minus 3. So you can kind of see how that happens here. Alternatively, another way to do this is you can say t equals to x plus 2, and then do a complete the square on that one. So y will equal to t minus 2 squared minus 4 plus 1, right? So you'll get that y will equal to x plus 2 minus 2 squared minus 3. So y will equal to x squared minus 3. So same thing. Either or is fine. Alright, so another thing about this is we need to talk about like intersections, right? So there is a distinction between when we talk about whether the paths will intersect and whether the things will collide. So how I like to think of it is if they will collide, right? It's like you and your friend go out, you're going to meet up at a certain direction at a certain time. You tell them, okay, we're going to meet at, 10:30 at Flinders Street Station, right? That's where we're going to meet. So you guys are going to collide because you have told them the time and you've told them the exact place as well. So you will meet at the exact same place at the exact same time. Compared to that, if your paths are intersecting, that doesn't mean that necessarily you'll be there at the exact same time. All it actually means is that your graphs will cross. So, for example, you pass through Flinders Street at 8:30 to get to school. And then your friend coming back from school, they pass through Flinders Street at 3:40 after school, right? So you pass through the exact same point, but you're not colliding because you're not there at the exact same time, right? So that's kind of the difference between the two. So if they ask us for paths intersecting, all we need to do is find the equations of each path and then just essentially equate them and see if it's possible to get an equation from there, right? If you want them to colliding, they must be at the exact same place at the exact same time. So you need to equate each component and then check from there. So we can do that. So let's say, for our points A and B, so let's work out our two equations. So x will equal to 2t minus 10, y will equal to 3, x will equal to 2, y will equal to t plus 4, right? So we can kind of see how this one will not really do anything in terms of its x value, and like these won't, both of them won't depend on each other, right? Because you can see how these ones are both separate. So therefore our goal now is going to be checking whether these two can equate or not. So 2t minus 10 will equal to 2, right? So 2t will equal to 12, so t will equal to 6. Now we do y plus 4 now. So y plus 4 will equal to 3. 3 will equal to, t will equal to negative 1, which is not possible, right? Because it will never reach 3. So therefore they will never be able to be at the same point anyway. Because if we want these to be at the same point, it must have t values which we can have the exact same coordinates for. So if we could try and equate those, right? So if we're equating the y coordinates, equating the x coordinates, if they paths intersect, they can just have the same coordinates. They might not have the exact same times, but you can kind of see that these times are not even possible in the first place. So you can say no, will not intersect. Alright, so if we have a specific rule defining our motion, so if the plane moves in a plane so that its distance from origin is always 3, i.e. a circle with origin 3, what we can do is we can call this a locus of a point rather than calling it a rule, or you can call it a rule, but rather than calling it a function, because it's not necessarily a function. And there can be different loci for the same shape, so you can describe it differently. And normally these are kind of distance based, and sometimes they have these points that we talk about, that it's like a stuck point and it's moving around it, or it's a stuck point moving with two things kind of moving at once, and that's how they get the point in the first place. So something like this, right? So you can see how this triangle is kind of moving along and it's stuck at a fixed point, right? And it's getting, further away from that point or closer away from that point. And you can kind of see how there's those 2 points, right, across the x-axis, and how these points are kind of changing based on that. But we have a fixed point right there. Cool. Alright, so if we have a Cartesian equation which is equidistant from this point, 1, 3, and the origin. So that's kind of similar to what was happening here, right? We want those points to be equidistant. So what we want is we want the line of the locus to be py, and we want them to be equidistant from these 2 points, right? So what we want is, if you can imagine like a line like this, what we're going to have here is we're going to have 0, 0, and the point 1 root 3. So 1 root 3, let's say it's here. Okay, so those are the 2 points that we want them to pass through, and we want them to be equidistant. And if we think about what is something that's equidistant between those 2 points, that would be the midpoint of those 2 points, right? So the midpoint of those 2 points would be equidistant. But they want an equation here, which means that we're not going to just have a single point. We're going to have multiple points along the line. So what we're actually going to have is, instead of just having 1 point, we're going to have a point along the line. So we're going to have a line which has to pass through that point, and therefore that line is going to bisect the line between those 2 points, right? So it's going to bisect the line between those 2 points. Another concept here is it's going to bisect those 2 lines, but how do we make sure it doesn't sway towards one side or the other? So the answer to that is that we can just find the perpendicular line, right? Because the perpendicular line will always continuously remain at 90 degrees to the line that we're drawing. So all in all, if we're trying to find a line which is equidistant between those 2 points, we need to find the perpendicular bisector of line from 0, 0 to 1, 3. Okay, so what that means is that we need to find a couple things first, right? So we need to find the perpendicular part and the bisector part. So the perpendicular part, we need to find the gradient. So the m equals to root 3 minus 0 over 1 minus 0. So essentially it's just going to be root 3 as the gradient. So your m perpendicular right? Your n perpendicular is going to equal to negative 1 on root 3. Okay. Then we need to confirm the bisector component. So in order to find the bisector component, we need to find the midpoint of those two lines. So it's just going to be 1 plus 0 on 2 and root 3 plus 0 on 2. So the midpoint is just going to be a half root 3. Okay, so now we have all the information we need, because now we're just going to have y minus root 3 on 2 will equal to negative root 3 on 2 times x minus a half. So what we're going to get here is that y will equal to negative 1 over root 3x. And we can do like, to make it a bit easier for us, we can probably times everything by root 3 at the bottom as well, so that we have 6 there. So we'll have that this is going to be, it would be like plus 1 on root 3. So if we times it by root 3, we'll have plus root 3 on 6, right? And we can convert this one as well, so we'll have plus 3 root 3 on 6. So y will be equivalent to negative 1 over root 3x, and then plus 4 root 3 on 6, which is going to be 4 root 3 on 6. So if we convert it to something a bit nicer, we'll get this is negative root 3 on 3x plus 2 root 3 on 3 as our answer overall. It's a bit squished, sorry. Yeah, so that will be our answer overall right there in terms of what we're gonna get. Cool, amazing, really, really good. Alright, let's go forward.